Okay, hello. Um, Today I thought we could do a nice little introduction to distance functions. So we're going to start with a brief primer on counting and sort of discrete things, and then we'll move to the continuous case, and then we'll build up this nice little theory of distance functions and do some worked examples with them in coordinate systems. So let's start from the Pythagorean conception of counting. So just to motivate it a little bit, the numbers that we see usually 1, 2, 3, 4, 5, and so on. These are actually like a really powerful piece of technology that was invented, not like at the start of mathematics, certainly early, but this is basically just a method of, really, excuse me. This is a method of really just being able to map something that is inherently meaningless to something with some sense of mathematical shorthand meaning. So, for instance, in Pythagoras' time, they used dots. So, one dot would be equal to 1, right? Two dots would be equal to 2. Three dots would be equal to 3. Four dots would be equal to 4, and so on. So one of the things that's nice about this dot representation that's sort of lost in this like numeric semantics, this sort of like, instead of equality, we could even just think of it as like a mapping, right? Where this is like really what this thing means, and then this is sort of like the numerical symbolic representation of this thing. One of the things that's lost in this is we don't get this notion of implicit geometry. We can think of these dots as something called number shapes. And that's really cool. We'll see a consequence of why, having sort of this like notion of shapeness or geometry is going to be really powerful when we start thinking about distance functions in particular, in a sort of shocking way, I would say. But yeah, I found this conception to be like actually worth a video, and I don't know, the idea kind of came to me, so we're just rolling with it. Anyway, so we have these number shapes, right? And so like what sort of consequences might we get out of something like a triangular number? You might ask. Well, I mean, we can look at the sort of like the pattern here. So we have, this is obviously the simplest triangular number, 3. And then we can build triangles from here, right? And now we see that 6 is also triangular. As is the number 10. If we just count this is 6 and this is 10. So we can actually see that we can build sort of larger and larger geometric shapes, right? And what we end up realizing is if we just add 1 to the previous base, then we get the next triangular number in the series. So we end up with 3, and then 6, and then 10. And we might be able to keep asking questions about sequences, like what would the next number in the triangular sequence be? Well, if we use number shapes, and this becomes immediately obvious, right? It's just going to be plus 5, because this base had 4, and then we need 1 extra one. So we need 1, 2, 3, 4, 5, right? So we can think of this sequence as like, what are all the triangular numbers? We can think of this sequence as 1, 1 plus 2. Sorry, got a little bit ahead of myself there. 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, and so on. And so like there is like this nice algebraic, that's a plus sign that looks too much like some other symbol. So let me just fix that. We see this nice, there we go. We see this nice algebraic, representation, which came very naturally from this like dot representation. So for answering really small questions, we can already see that there's this immediate sort of like mathematical intuition or I guess like niceness. It allows us to think about a way of doing mathematics. I'm just gonna make sure this is clear. This is an A. Doing mathematics from like sort of a geometric or visual perspective, but get to something algebraic, and that's really nice. Okay, so like that was the first example, but I'm really interested in distance functions. That's what we've kind of been talking about, or what I've been hinting at. So I want to show sort of something visual for something else. So okay, the Pythagoreans were really interested in triangles, right? Everyone knows that. The Pythagorean theorem is a squared plus b squared is equal to c squared, which is equivalent to c is equal to square root of a squared. A to be the sort of distance in the x direction on a coordinate system of x2 minus x1. And we can set b equal to, in the y direction, the same thing. And what we end up with is this familiar representation. And I'm going to use d here instead of c to denote this as a distance function. Right, so we get this sort of natural distance function from this conception. So this is, I think, the typical way that we usually think about the Pythagorean theorem and how it's sort of taught in school. But there's another representation of this that I really, really, really like. And it's much older, so I'm just going to kind of go through it, and I hope you'll enjoy it. I'll talk a little bit about motivating this and sort of building up some theory around this as well. But for right now, I just want to sort of have it in mind or remind you what a distance formula looks like, and then we'll talk briefly about metricization and other bits and pieces that are also, like, I think, just really interesting. So the Pythagoreans were really interested in this when they considered triangles, like I said before. They were really interested in this because you could sort of take like this x direction, right? I'll just give the geometric representation before we move on, actually. And that's A, and this is B, right? And so that's how we map this x1 minus x2. So in the x direction, I guess, let me change those labels just to keep everything consistent. Yeah, it's really tricky when you actually have to think about semantics. Anyway, so we can think about it this way, right? And so this is that distance d that we were talking about. Okay, so that gives you some like continuous representation, sort of like reminding you of that. Okay. So now we can really move on to the thing that I want to say, and we're just going to sort of, oh, you know what? I'll leave this here just so you have like a reminder. Okay, so here's the fun thing. So notice, right, with this geometric representation of a number, we can do the following. Most people don't know this. The reason why when we take a power and we take it to the second power, when we take a base to the second power, we call it squaring. That's because we can draw a square. So this is squaring. And this is square roots. And yeah, these two operations I think become really, really obvious in like sort of the discrete analog. And it works for anything, right? This is not just specific to 2. Okay, so you might ask yourself, what's the rule here, right? What's the rule that we're really thinking about when we think about this? Well, the rule is for squaring. Okay, that's a bad cue. Oh my God, wow. I'm just really messing up my cues today. I don't know what's going on. You know what? It's this surface. It's actually kind of hard to write on. So I apologize, but yeah. Okay, you have to be really, all right, careful about that. So squaring, right? So the rule is create as many rows as there are columns, right? That's the like sort of finite rule for squaring, which makes some intuitive sense. And then square roots is literally take one column, assuming all columns, that's an n, sorry, are of equal length. Or no, sorry, take one column, sorry, that's supposed to be rows. That should be rows. One row. Yeah. Yeah. So that's the idea, right? So doing a worked example, we'll just do 3 because it's such a pain to draw more circles than that. Right? So this is the squaring function. And then if we want to go back, I'm literally just going to circle one of these and call it a day. So if there's a way to organize your number shape such that you have an equal number of rows and columns, then we say that the number is square. And this is like a really nice piece of technology. So the reason why I bring this up and its relationship to distance functions, I think should hopefully be obvious, but I'll just sort of restate it. So we have a squared plus b squared is equal to c squared. Well, now we can very easily calculate squares, but more importantly, we can very easily calculate certain square roots. And that is in and of itself very powerful, right? Because we have this like obvious fact. We have this obvious fact, right? We can take this square root very easily. And now we have this really fast operation that's visual to take square roots and squares. So we have fast square and fast square roots. And I mean fast in a very specific sense. Intuitive for humans, right? So like, it doesn't take sort of like an algorithmic procedure for calculating the square roots. You can just sort of like do this really quickly, and you can kind of gut check it for small numbers really fast. Now, obviously, as your numbers get big, right, as n gets large, this can be hard. But for small numbers, this is like really, 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 really fast. Anyway, okay, so that gives you like this sort of discrete analog for a distance function. And yeah, this square root is both is literally it. This is like, I mean, well, it's actually this thing. This is right, like this is the full thing. But we can now take distances of number shapes, and we can do it in almost a trivial sort of way. So that's really nice. Now, of course, it's like very painful to work with these dots in practice. So we'll stick to sort of like the numerical representation that we have all sort of grown up with when dealing with this. But like it's pretty nice, right? Like it's pretty nice. So okay, we're gonna start with like a couple examples, and I'm gonna do a really simple one, just using sort of standard geometry. But before I do that, actually, let me just sort of make an equivalent. So right, so like we can say that, and this is just me stating a fact. I mean, I think this will be immediately obvious. We can say that the number shapes are embedded in the real line. Yeah, so there is like this relationship. So like if we think of number shapes just always as being a line, right? Always being kind of like continuing forward, and each dot sort of represents a number. So this is like 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's 10. Then we have this like equivalent representation of the number line. Yeah, and we would consider this N, and we would consider this R. And these are Blackboard numbers. This means like Z plus, which is equal to positive integers. And this is the real numbers, right? And the reason why we like the real numbers is because they're sort of like the least complicated infinite uncountable number sets. So we'll take a little care to talk about this, right? So like we have now distance functions on sort of like dealing with just strictly discrete values, but there is this continuous analog, right? And I mean, I've already defined it for you. It's literally this thing that we've been kind of dragging is not the best, but this is the continuous thing, right? So there's no gaps, there's no holes in this. Any real number can be equal to D, and that's nice. So yeah, the danger or the downside, I guess, of this integer distance, you might think, well, this is great, right? But there is a downside to this integer distance. Well, so like, what do you do with things like square root of 2? In the integer distance, this just doesn't work. It's not possible, right? And this arises really naturally, as I think will be obvious. So that's how you get the square root of 2, right? So if we start with a unit distance, just literally a unit distance, where like you have like, if we're considering like a discrete Cartesian coordinate system, right? And we just want to go 1 in the x direction and then 1 in the y direction, then we're going to end up with square root of 2 here, which is not really possible. You can't do that. It doesn't exist in this number system. That's not possible in a discrete number system. So, you sort of need the reals to really talk about distances, but sometimes you can like fudge and approximate, and this discrete thing can be really, really fun to work with. Okay, but let's look at some functional distance functions in the real Cartesian coordinate system, right? So just a reminder really quick, this is what it looks like, direction, y direction. But yeah, so let's just do some examples. So, okay, so question 1. All right, suppose we have the points 1, 1, and 4, 5. What is the distance between them? Right? So you can ask that question. You can ask that question. And you can answer it in a very straightforward way, right? You just apply the formula, you plug and check. So we have 4 minus 1 squared. And this is hopefully just, intended to be like really kind of a reminder. Just to go through one mechanical example, you take the square roots, and then you end up with 3 squared minus 4 squared, which is equal to 9 plus 16 squared, which is equal to 5. This is 25 down here. So yeah, square root of 25 is 5. Okay, so we can ask a more interesting question. Question 2. What is the distance between AB and BA? So can we define, sort of like we did above, with the square and the square root, like a shorthand algebraic fact that we can make use of forever after? Well, we can start by simply like plugging and chugging and applying the formula, right? So B minus A squared plus A minus B squared. And this is equal to B squared plus 2, minus. Always mess that up. Minus 2AB plus A squared, right? That's the first term. Plus A squared minus 2AB plus B squared. And we take the square root of that. So we can add up some terms. 2B squared minus 4AB plus 2A squared. Taking square roots, and then we can pull out a square root of 2, and we end up with B minus A squared taking square roots, which is equal to square root of 2 B minus A. Isn't that really fun that we end up with sort of like this unit distance times the B minus A, and this distance like seems fairly obvious. So we have this nice shorthand here. Anyway, that was like all I really wanted to go over, just like a nice conceptualization and then a couple of examples. I hope you enjoyed it. Okay, thanks.